Hello, my name is Paula Perez. I am the product manager of the IMS 7f-GEO. CAMECA is, as you know, a manufacturer of magnetic sector mass spectrometers. This talk will show applications of the CAMECA IMS 7f-GEO to stable isotope analysis. This is the outline of my talk. I'll start with a small introduction to the SIMS technique. Then I will show the key features of the IMS 7f-GEO and applications of this instrument, starting by a small overview. And then I will show 5 different studies based on stable isotope measurements performed with the 7f-GEO. To finish, I will show an overview of the SIMS models proposed by CAMECA for Geosciences. A brief introduction to the dynamic SIMS technique. When a solid sample is bombarded by primary ions of a few keV energy, a fraction of the particles emitted from the sample surface is ionized. Secondary ion mass spectrometry, SIMS, consists of collecting and analyzing these secondary ions with a mass spectrometer. SIMS provides a local analysis of any type of solid flat material that can be maintained under high vacuum. Both elemental and isotopic information can be obtained for all species in the periodic table, from hydrogen to uranium and beyond. Dynamic SIMS is a destructive technique by its nature, as it is based on sputtering of material. It utilizes a high-dose ion bombardment that is able to erode successive layers of the sample, providing information about elemental and isotopic composition over depths that can range from nanometers to tens of micrometers. Still the most sensitive surface analysis technique available, dynamic SIMS provides elemental detection limits that can reach parts per billion for many elements. SIMS has been largely used in the geosciences field because of its high sensitivity, which is required for high precision measurements and/or low detection limits, because it provides both elemental and isotopic information for quasi all elements of the periodic table. It provides in situ analysis of any solid flat polished surface with a high spatial resolution from tens of microns down to the sub-micrometer scale. Therefore, SIMS allows microanalysis of small minerals within their petrographic context or domains in single crystals. Magnetic sector SIMS instruments provide the best performance for dynamic SIMS analysis. This sketch shows the operating mode of a magnetic sector SIMS instrument, the CAMECA IMS 7f-GEO. There is a primary column with 2 ion sources, an oxygen ion source that enhances the ionization of electropositive species, and a cesium ion source that enhances the ionization of electronegative species. It is based on a continuous primary ion beam bombardment, as well as on a continuous secondary ion extraction. Combined with a strong extraction field for the secondary ions collection, it offers optimized instrumental transmission and thus low detection limits. In magnetic sector SIMS instruments, the secondary ions, which are characteristic of the composition of the analyzed area, are separated in a magnetic sector analyzer according to their mass. The design of CAMECA magnetic sector SIMS instruments is based on a double focusing mass spectrometer design, that is, the coupling of the magnetic sector with an electrostatic sector. This type of mass spectrometers can separate most interfering species using high mass resolution conditions while keeping a wide energy passband. The IMS 7f-GEO works in monocollection mode, secondary ions being acquired one by one by scanning the magnetic field as shown here. Both electromultiplier and Faraday cup detectors are available. Dynamic SIMS using magnetic sector SIMS instruments are well adapted for elemental and isotopic analysis in inorganic materials. Dynamic SIMS is ideal for depth profiling when low detection limits are required, including for light elements. When the depth to be sampled is very large and good sensitivity is required, the analyzed depth ranges from few nanometers to few tens of micrometers. For ion imaging analysis, when high mass resolution together with high sensitivity are required, and for high precision isotope ratio measurements. Analysis can be performed with high throughput and productivity. These capabilities have ensured its regular use in fields such as microelectronics, life sciences, and geology. A brief introduction to the IMS 7f-GEO instrumentation. The IMS 7f-GEO is a monocollection compact SIMS model which has been designed to meet the high precision, high throughput requirements of stable isotope and trace element analysis for the geosciences community. We can see here the synopsis of the 7f-GEO. On the left, the primary column, equipped with 2 ion sources, oxygen and cesium, sample introduction system, the ultra-high vacuum analysis chamber, and the mass spectrometer based on the coupling of an electrostatic sector with a magnetic sector. Magnetic sector has fast peak switching capabilities, which provides high throughput and improved precision. The 7f-GEO is equipped with a specific detection system. It's a monocollection system based on 3 detectors, 1 electromultiplier, and 2 Faraday cups, FC1 and FC2. The 2 Faraday cups have state-of-the-art electrometry, which guarantees low noise and stable baseline, which is very important in order to achieve high reproducibility and high throughput. So why a detection system with 2 Faraday cup detectors? We show here an example of a measurement of the 18O to 16O isotope ratio, for which the analysis precision needs to be better than 0.4 per mil. If the 18O signal intensity is of at least 2 million counts per second, then we can see this table that using FC-FC mode is very interesting because of the much shorter acquisition time, about 1 minute, to reach 0.4 per mil precision. Therefore, for high precision, high throughput isotope ratio measurement, Faraday cup detectors are preferred to electromultipliers, provided that secondary ion intensities are high enough. We can see here experimental data obtained for oxygen isotope analysis on the 7f-GEO. The oxygen isotopes are measured using a cesium primary ion bombardment, detection of negative secondary ions. The measurements were performed on a silicon quartz disk, which is an insulator, so the electron gun was used for charge compensation. The analysis area was 10 by 10 micrometer square. Measurements were performed using high mass resolution, with 16O being recorded on FC1 and 18O on FC2. The 2 Faraday cups have 2 different resistance values in order to decrease the noise level on the 18O signal. A resistor of 1E11 ohm is used. 3 series of 10 spots were performed over a diameter of 15 millimeters. We can see here the results. So knowing the counting statistics for these measurements and the total integration time of 56 seconds, the expected precision for the isotope ratio 18O to 16O is 0.4 per mil. We can see here on the graph the 3 series of 10 spots performed repeatedly, and we obtain a standard deviation of 0.37 per mil, which is in perfect agreement with the expectation. I will start by a brief overview of the 7f-GEO application. I will show here a few examples of 7f-GEO applications. For example, for geochemistry, there are studies of spot isotope analysis, for example, sulfur in pyrite. We see here an example of carbon in-depth isotope analysis in calcite. I will show it more in detail afterwards. We can also perform scanning ion imaging. For example, here gold mapping in arsenopyrite. And it is also used for elemental analysis, for example, rare earth element diagram in melt inclusions as shown here. Cosmochemistry is another field that can be addressed with the 7f-GEO. We can see here an example of oxygen 3 isotope analysis in a meteorite quasicrystal. And of course, we can also perform analysis in different types of materials using depth profiling or ion imaging capabilities. Here, for example, we see titanium-rich precipitate in a metallic alloy. And now a few examples more in detail. In this first example, we show the measurement of boron and oxygen isotopic compositions in tourmaline. Aqueous fluids exhaled from crystallizing granitic melts during emplacement into the shallow crust can lead to a broad range of geological phenomena. The Devonian granites of western Tasmania contain abundant tourmaline-rich features, including orbicules, patches, cavities, and veins within their roof zones. This study is based on SIMS, boron, and oxygen isotopic analysis of tourmaline from West Tasmanian granite. The goal was to investigate the role of volatile exsolution in the late crystallization stage of felsic magmas, evaluate the origin of tourmaline quartz orbicules, and elucidate their relationship with tin mineralization. We can see here the results, the histograms showing boron and oxygen isotopic compositions of tourmaline in different textural assemblages. Data show that tourmaline grains in magmatic hydrothermal features from western Tasmanian granites have distinctive compositional and isotopic zoning. The external precision evaluated from analysis of the Elbaite standard was 0.2, 0.3 per mil for boron isotopes and 0.2, 0.5 per mil for oxygen isotopes. In this study, the sulfur isotope behavior of Archean sedimentary rocks was investigated. Recycling of surface-derived sulfur into the deep earth can impart distinct sulfur isotope signatures to magmas. The details of sulfur transfer from sedimentary rocks to magmas and ultimately igneous rocks through metamorphism and devolatilization and/or partial melting is difficult to trace. In order to investigate this process in detail, multiple sulfur isotope SIMS analyses were performed on sulfides from the Archean Ghost Lake batholite and its surrounding host metasedimentary rocks of the Superior Crater in Canada. We can see here the histograms that show the delta 34 sulfur obtained by SIMS for sulfides from different samples. The in-run precision was 0.02 per mil for delta 34 sulfur and 0.06 per mil for delta 33 sulfur. The external precision was between 0.2 and 0.6 per mil for both delta 34 sulfur, delta 33 sulfur, and big delta 33 sulfur. Here, another example of sulfur isotope analysis, this case of multicrystalline iron sulfides. Iron sulfide minerals, particularly pyrite, represent a substantial geological reservoir of sulfur. Sedimentary pyrites have proven to be invaluable archives for reconstructing local environmental conditions as well as global-scale changes in biogeochemistry. In this study, a method based on SIMS scanning ion imaging has been developed that provides the spatial resolution necessary to measure inter- and intra-grain delta 34 sulfur variability in microcrystalline pyrite. We see here the published results. In A, the optical microscope image, and in B, the SIMS scanning ion imaging obtained over a field of view of 50 by 50 micrometers square. In C, we see the corrected sulfur isotopic composition for the fragments shown in B. The data obtained on sulfur isotopic standards showed little inter- or intra-fragment variability in the delta 34 sulfur value, with a fragment-to-fragment reproducibility of plus or minus 2.3 per mil. Therefore, the method is suitable for the detection of delta 34 sulfur variations that may exist within or between sedimentary iron sulfide grains. An example now of a measurement of carbon isotopes in calcite. Near equilibrium calcite dissolution in seawater contributes significantly to the regulation of atmospheric CO2 on 1,000-year timescales. Despite many studies on far from equilibrium dissolution, little is known about the detailed mechanisms responsible for calcite dissolution in seawater. In this study, 13 carbon-labeled calcites have been dissolved in natural seawater. The evolving seawater delta 13 carbon traces mass transfer from solid to solution. Dissolution will add 13 carbon to solution. Precipitation will add seawater carbon, mainly 12 carbon, to the solid surface. We can see here the SIMS carbon isotope in-depth profiles measured on the 13 carbon labeled calcite solution. 3 different experimental conditions were used. We can see that in the first 50 nanometer of these profiles, the solid red curve transitioned from a super saturated composition in blue to an unreacted composition in yellow. Data confirm the presence of precipitated material even in undersaturated conditions. The time evolving enrichment of delta 13 carbon in solution is a direct measure of both dissolution and precipitation reactions across a large range of saturation states. In this last example, we show a study of hydrogen and copper isotope analysis of turquoise. The hydrogen isotope system is used extensively to provide information on the genesis of minerals, for example, source of fluids and mechanisms of precipitation. The copper isotopic system is less well understood, but has the potential to provide valuable insight on mineral precipitation, particularly supergene copper-rich minerals. This paper presents a rapid and precise SIMS method for measuring hydrogen and copper isotopes in semi-precious gem quality turquoise. On the left, we can see the delta D of 4 turquoise standards for 3 sessions. On the right side, the delta 65 copper of 4 turquoise standards again for 3 sessions. Delta D and delta 65 copper SIMS analysis precision was plus or minus 5 per mil for delta D and plus or minus 0.5 per mil for delta 65 copper. This study demonstrates the potential of SIMS applications in identifying gemstones provenance and understanding the genesis of turquoise deposits. I would like to finish this talk by a short overview of CAMECA SIMS models for geosciences. In this talk, we have presented the IMS 7f-GEO, which is a compact monocollection SIMS model. Its strengths are its versatility, its high throughput, and a specific detection system for high-precision stable isotope measurements. Isotope measurements can be performed with a precision down to sub-per-mil, but it can also be used for depth profiling analysis as well as scanning ion imaging, with a lateral resolution down to sub-micron. There are many applications in geochemistry, cosmochemistry, as well as material sciences and nuclear sciences. CAMECA also offers large radius SIMS instruments. Here we can see the IMS 1300 HRQ. Its key features are its isotopic multi-collection system, the possibility to use high beam current, and its high sensitivity at high mass resolution. This instrument provides the best performance for isotope ratio measurements with a high precision down to 0.1, 0.2 per mil. Its applications include geochemistry, cosmochemistry, and nuclear safeguards. CAMECA also proposes the NanoSIMS 50L. Its main features: isotopic and elemental multi-collection system, a beam size down to 50 nanometer, together with high transmission at high mass resolution as well. This instrument provides imaging with the highest lateral resolution. There is a wide range of applications: geo and cosmochemistry, materials, cell biology, environmental microbiology, among others. With this, I will finish now my talk. If you have any question, please do not hesitate to contact me at this email address. Thank you so much for your attention.